welcome back to the class of differential equations and matrices. Today we are moving to section 4.4 about second order linear differential equations with constant coefficients. And if you check closely, I hope you see the difference between this new topic and the other topic we covered in the previous sections. The keyword is homogeneous. This time we are considering pretty much the same kind of differential equation, but it is non-homogeneous. And to get started, I'm going to work with one relative simple example first, so you can have some idea. Okay, so we want to solve a second order linear differential equation with constant coefficients and not homogeneous, because the right hand side clearly you can tell it is not homogeneous. So to handle this type of differential equation, basically you will have to consider at least 3 steps. First, the step I did here is I pretend this differential equation it is homogeneous. This differential equation it is homogeneous. So according to the topic we covered from 4.2 and 4.3, and the characteristic equation it has a characteristic equation, right? It's a quadratic. And indeed, it can be factored as r minus 2 and r plus 1. So I said here, there are 2 roots. R sub 1 is 2, R sub 2 is negative 1. And then again, according to the discussion in those 2 sections, okay, we can generate the solution for the homogeneous differential equation. So I denote this as y sub h. Y sub h, it is a linear combination of these 2 exponential functions. And also it's worth to mention, if you are watching this video, y sub h, indeed, it is not a solution of this original differential equation, but it is part of the solution, okay? So this is our first step. The second step is we really want to generate an actual solution for this differential equation. We really don't know a lot about those derivatives yet, but we see the right-hand side, it is linear polynomial, right? The right-hand side, it is linear polynomial. So maybe it may not always work, and maybe what we can assume here is there is an actual solution, and we call this actual solution as a particular solution. It's denoted by y sub p. Maybe there is a particular solution because the y term, and certainly the second order derivative and the derivative, they all play roles here, okay? I say it's a reasonable assumption. Maybe there's an actual solution, which is just a linear polynomial. Certainly, you don't want to say it may match precisely to the right-hand side. Yeah, usually it does not. So I say the particular solution, it is AT plus B. A and B are the coefficients. By the way, it's worth to mention, these are really unknown coefficients, or precisely if we follow the textbook, these are so-called undetermined coefficients. So the remaining task is to find out A and B. Keep in mind, we do have this differential equation. So what I did to find out A and B, I calculate derivative because it's linear, so the derivative is A, right? And the second order derivative is 0. So I put everything, second order derivative, and y sub p, everything together into this differential equation. Take a look at what would happen. Y double prime minus y prime minus 2y is, okay, double prime 0, so I put a 0 there. Y prime, that's a there, minus 2y. So I distributed 2 into both terms. And then I say the keyword it is a polynomial, a linear polynomial. So somewhat I arrange the polynomial in the standard way, in the descending order, starting from the term t and then with a constant. And I know this polynomial really will have to match the right hand side, right? And there are uncertainties. It will have to match for any t value. And both a and b are unknown. So what I decided here is somewhat it is kind of it is kind of we kind of use a strong assumption here. Because this left hand side will have to match exactly the right hand side for t. So what I did here is I say term-wise, because the corresponding terms, the coefficients of the corresponding terms will have to match. So I simply say that negative 2a will have to match to 2, and the negative a plus 2b will have to match 1. And sometimes it is not possible, and if it is possible, then we are done, right? So indeed, it is possible. From this assumption, we can make this a as negative 1, and from the second assumption, we can make b as 0. So indeed, it works perfectly fine. And we said this y sub p is a particular solution, it's a linear polynomial, and we figured out a is negative t, b is 0. So which really means y sub p, it is negative t. It is an actual solution, and precisely it is called as a particular solution. Okay. And now if you followed me closely, I said in the step 1, we got something part of the actual solution. It is denoted as y sub h, homogeneous solution. And the step 2, we got a particular solution. And then step 3, somewhat, it is a rather easy thing. You're going to add the homogeneous solution and the particular solution together. That forms step 3. Okay. In general, the solution of the original differential equation, it is formed as y sub h plus y sub p. Y sub h plus y sub p. And indeed, it can handle a lot of problems for this kind of second order linear differential equation with constant coefficients and non-homogeneous. So this is, I think I directly quoted from the textbook. Okay. And then one particular thing you may want to know here is this y sub h, it is the solution of the corresponding homogeneous differential equation, which was covered already in section 4.2 and 4.3. And particular solution, y sub p, it is a particular solution, and it is an actual solution. This should be written as y sub p. It is a particular solution. And the particular solution, it is generated to fit the right-hand side. So for now, I just want to know there are 3 cases for the right-hand side we need to consider. Okay, the first case, when the right-hand side, it is polynomial. Basically, what we need to assume here is the right-hand side will have to be polynomial of same degree. When the right-hand side, it is polynomial, then the particular solution, it is assumed as a polynomial of same degree. And the second case, when the right-hand side, it is an exponential function, and then you are going to assume the particular solution, it is of the same kind of exponential function, but may carry different coefficients. The third case, when the right-hand side involved with trigonometric functions, sine and cosine, and then you're going to assume the particular solution with corresponding trigonometric functions too. So these are the 3 cases you need to remember. Okay, and certainly you need to know the three steps as we previously outlined. Well, it's right here, those three steps. And indeed, consider example 1 as I just explained. It is for case 1. Hey, thank you for watching. I'll see you next time.